from
you don't know where you're going to
the
end up.
area, you know.
And that's a big fancy house. And so, you know, you're 2 hours away from work.
Exactly.
And you gotta sell it. It's not that bad. I'm like 12.
Case I ever have I'm probably ready to start.
Good morning and welcome. My name is Scott Lytle. I'm the chapter chair for the IEEE EMC Society here in Southeastern Michigan. And I thank you all for your attendance today. I know it's really cold and nasty out there, but at least it's not snowing. So we got that going for us. I'd like to start with thanking our sponsors today. We couldn't do this without our sponsorship. So we have, first of all, our facility sponsor is Barry's. Thank you, Barry, from MPS. Peggy Gerard. Peggy's in the back there. Wait, Peggy. Peggy's sponsoring pizza lunch. And finally, we'd like to acknowledge Rhodey and Schwartz for their participation. They brought in a lot of demos and folks to do the demonstrations today. We do have water and coffee in the break room. It's just outside of that door. The restrooms are right over by the elevator. Candace, do you want to do the rest of your introductions? Candace wrote this up, so rather than botch it, I'll just let Candace do the rest of this.
Thank you so much for coming. My name is Candace Suriano. Scott Lytle and I helped organize the workshop with the help of Mark Stefka, Bob Adams, Barry Self, and Rhodey and Schwartz. When I first started in an EMC lab, I walked in and I was like, oh, what kind of filtering do we use? And they were like, there's no filters in EMC. And I was embarrassed. By the way, I did find the filter. It was the right question to ask. It was a Gaussian filter and the intermediate filter. And that's why we do this, because EMC is magic. It's action at a distance, and it's not taught well in schools. So we come and we give you a piece of what we've learned so that we can all grow as a community. And so I want to thank the presenters, John, who puts up with me, Professor Mark Stefka, expert Bob Adams. These people are doing this no pay. We just do it because we care. And then we want to thank the people from the Rhodey and Schwartz Graduate Development Program, Sophie Platten, Grace Root, Maeve Ryan. And so you want to help me start?
Yeah, great to switch. Oh, this is the agenda for today. It was online, right, but we'll bring that up.
And if you stay to the end, there's a drawing.
You can get what's left of a bag of lunches.
No, actually, it's Amazon cards.
I'm going to try and bring up the angles. Okay, she said it's action at a distance. It's also magic, and it's demos that never work. So we'll see. It's been sitting out in the car all night, so the batteries are probably dead. Not sure if it's oh, that's sad.
It's supposed to explode, but
I always have a backup. I learned a long time ago that with these demos, I can't do them at the place. So that's why I started making videos. I should have. You can just So
So my part is the fundamentals of EMC.
let me get that thing out here.
And of course, we really want to thank AP Americas. They've got some gorgeous chambers here, and MPS, who has given us a place to have it so it could be cheap. These are great books. And look, right there is one of our speakers, Mark Stefka. This is the most used EMC textbook, Introduction to Electromagnetic Compatibility, and Mark comes next. Here's some good books on signals, McGillow and Cooper, and I love Sean's outlines. Here's where you can find a lot of this stuff done. Now, everybody knows action at a distance.
Yes, we can't hear you in the back.
Can't hear me.
There's no
Oh
microphone.
dear. Is the microphone not working
The microphone's up
I can
there.
hear you fine, Candace.
over there?
Yeah, Mark can hear you. He's the only.
Oh, Mark can hear me. Whoa, this is great.
No, I think though, if we turn this one off and turn your computer one on, it would help.
Well, I can try to be louder. How's that?
The problem is in the room, I think.
Yeah.
There's no speaker
Okay,
in the room.
can you guys hear me
No, our
now?
speakers.
Eric, can you hear me? Oh, good. Okay. I'll try to use a mom voice, which I don't use all the time. It's okay. We're good. I'll just
Okay.
use
Use a
I'll
mom
use
voice.
my mom voice,
I think I'd
and
probably
Eric
figure
can
something out,
tell me if I no longer sound like a mom.
but- Okay.
Well, and just for the record, if you're gonna use your mom's voice with me, it has to be Eric Paul. That's when I know I'm in trouble.
So it used to be in the beginning of EMC
I know,
that people would take things and park them
We gotta get that
near
fixed
the
before we get
radar
outside.
at the airport to find out what happened.
And I can improve.
But there are things that happen. There's a fuse in your injection seat. Radars melt fuses, which is why it used to be at an airport, there'd be all these cars parked and they would have things in them. So I want to tell you why I care about EMC and why you should care. How do we measure it? Some of the key elements and EMC for everybody. Okay, what makes EMC? So EMC just means that if I have two things next to each other, one doesn't stop the other one from working. And what are the two sides? Well, there's emissions. There's, if I have a blender, it doesn't affect, or a mixer, it doesn't affect like your lights, doesn't affect your, and then there's immunity. And immunity is very important, especially if you wear polyester or you have long hair. So who cares? Governments, would you like to fly an airplane that has problems with EMC? No. Automobile manufacturers. People who have interference on their radios. Hospitals. Have you ever seen someone wired up for an EKG? Those are antennas everywhere. Oh, and lawyers love it. Causes problems. Any wire, a switch, that's a broadband noise. There's arcing. Circuit board design, cycle rate of software. How many people knew that the cycle rate of software sends out a, oh, I'm so glad Bob knows. Very good. And your name is?
Matt.
Matt Cook, cool.
This guy
Shag
knows
carpeting.
too.
And long hair. Okay, what do you need? Electromagnetics. Signal processing, communications, analog electronics, digital electronics, PCB, layout, software. And of course, analog electronics includes your layout because everything on the board is an element. So this is just, what do? We do radiated tests. We do conductive. We looked at transients. We look at immunity, conducted immunity, and electrostatic discharge. So what are the kind of common things? So conducted transient emissions. If you have a problem, you unplug your blender, your juicer. Conducted RF emissions. So if you run your blender, your juicer while watching TV, if it's too close to your tablet, you might have some problems. And Christmas tree lights, sparkly kind, they slow down your Wi-Fi. So radiated RF emissions, magnetic field emissions. Has anyone ever taken a magnet near their computer monitor? Yeah. I can tell you guys are engineers. How much fun. So why should you unplug your computer during a thunderstorm? Well, not only could your house get hit by a lightning bolt, which we had, which by the way, melts everything. You should unplug it because of the transients. And yeah, don't place your iPod in a microwave oven.
You can tell how old these slides are.
You're right. The gray hair is real. Why should you not run a network cable next to house wiring? Or if you're in a church, never run air conditioning next to any signal cables because they have the chopping of the waveform. Absolutely destroy it. ESD, do you really have to stay outside your car while refueling? The American Petroleum Institute used to have some videos showing what happens to young women with long hair and polyester when they go in and out. It was not good. So what kind of things do we use? We like reverberation chambers. And of course your microwave is like a tiny reverberation chamber. Semi-anechoic, anechoic chambers, they can have tiles, they can have cones, and it makes it more like you're out in the open. Not exactly, but close. So what kind of equipment do we use? We use antennas, probes, receivers, and spectrum analyzers. We use artificial networks, oscilloscopes, transient generators, ESD guns. That's the most fun. John has a demo. He made his own little ESD gun. Power amplifiers. And one thing you may not think about, your standard. That is very important. Okay, this just shows you where we have, okay, this is, you use the monopole, use a loop antenna, so what does time domain mean? It means that I can see things as they start and stop and change as a function of time. Frequency domain, think of a piano. Can you still hear me, Eric? Okay, good. Think of a piano. You're looking at everything in the frequency domain. What kind of signals do we have that cause problems? Power lines. Someone using a signal generator. Radio, TV, communications, cell phones, radars, digital. Did you know that you not only have the digital signal, but you have the envelope signal? So when you're looking at something, you're like, oh, it's not gonna mess with it. Yes, it will, because your electronics will read the envelope. Transient is one of the most fun things. any sort of switching. And of course, we have my all-time favorite, the thermal noise from the universe. And it does make a big difference. You can actually see when there's a celestial event. So DC motors cause a lot of broadband noise. Anytime you have arcing, so anytime you switch something on and off, you have a broadband noise, which, it's the direct delta, and then you have noise across the spectrum. Narrow band noise is very interesting because it has harmonics. You have radio stations, you have communications, microprocessor clocks, and Bob will tell you how you spread that noise across the spectrum. So what kind of words do we use? You could say, what's your resolution bandwidth? What's your video bandwidth? Oh, what's the dynamic range of this? What kind of attenuation do we have? What's the reference level? Do we have a preamp in here? Ooh, and here's a Rodian-Schwartz word. Do you have a pre-selector in there? Oh, but impulse response. What's your impulse response? Have you done a time domain scan? What's your fast Fourier transform? And of course, CISPR 16, which has been updated since we wrote this. Okay, so decibels. We always talk about decibels. We're using logarithms, so we can use big numbers and small numbers. So small differences of small signals and big differences of big signals. We're just saying, okay, so I can put everything because it goes like this. What kind of broadband noise? We talked about broadband noise, about a motor. Okay, you can have something happen every time the motor goes around. Or you can have incoherent broadband noise. That's more exciting to deal with. The power density is constant over frequency. The amplitude increases by the square root of the bandwidth. So your bandwidth, you might have something that's okay. If you have a tiny bandwidth, you open that up, you've got a problem. So bandwidth is not the measure of my waist. It is the frequency width of a filter. And you can think of it as a funnel. So like I said, when you have more, you open that up, you've got more coming in. And a 3 dB bandwidth is not the same as a 6 dB bandwidth. And would a 6 dB bandwidth have more in it than a 3 dB bandwidth? Yeah. So how do we modulate these? A narrow band signal of one frequency is a continuous wave. The way we change things is by using a carrier frequency. And sometimes the carrier frequency is continuously altered. This was one of the first ideas of SPIES. It's a spread spectrum. Communication signals are attached by modulation. Amplitude modulation. Is amplitude modulation or frequency modulation? Which one is easier to mess with? Do you know, Matt?
Amplitude?
Yes, because that's what we're looking at. In frequency modulation, it's harder to mess with. And of course, pulse modulation turns the carrier on and off according to a digital signal, and pulse modulation is very noisy. Okay, here's an example of a narrow band signal modulation. narrowband noise. Broadband noise, any sort of switching transitions. And like I said, when you have the pulse width, your electronics will read the envelope as well as what's in it. So depending on where you're looking, there can be problems. Square wave. Square wave is exciting because it has so many components. When you look at the Fourier transform, it's like out forever. And so you have noises from something in low frequency at higher frequencies. And you can see the pulse frequency, the carrier frequency. And a sine wave, ideally, you only have one frequency. There's the exponential delay. How do we get from one device to another? Well, if you have polyester, it's ESD. There's capacitive coupling. Inductive coupling, that's transformers. We have radiation. So anytime you have loops, you have this circuit board that picks up the, as I type into it, there's loops underneath the whole thing. And it picks up everything. Electrical coupling, that's an antenna. And of course, radiation. So what do we want? Well, ideally, we would like a differential mode current. But normally that's not what you get. You actually get this, which is called a common mode current or an antenna current. So wiring, one of the things we used to do is we used to have a little AM radio and we would trace the wires. So any wires act like an antenna. So hopefully what you learned is what EMC is made of: emissions immunity. Broadband noise is over a large frequency. Narrowband is one frequency, or one frequency in the harmonics. So you can have coherent, incoherent. There are 3 types of narrowband modulation: AM, FM, pulse. And how does something low make a noise in something higher? So the harmonics, because when you have one, you don't really have one, you have a whole set. You have the pulse modulation of a carrier. And so a cell phone, that signal, you can have a speaker read the envelope. And so you can have problems with higher frequency things at low frequencies, audible frequencies, because of the, okay, so common mode, you have the same current on both wires. Differential mode, that's what we want because it helps cancel out the signal. How do we get rid of conductive problems? We reduce differential mode, you can reduce common mode. So how do we introduce noise? Direct conduction, current injection, capacitive coupling, and radiation. And this is Dr. John, who has known me for a long time.
Yeah.
Cool.
All right, we'll try to run through this. Some of you are experts in EMC. Some of you don't have any background in EMC. This is all aimed at you who don't know anything about EMC. Okay, this section is about how do we eliminate EMC problems. So we have a few case studies that we go through that we've had over the years. These are things that happen to us, not at work. They're not really high-tech things, but they're interesting and they show points about EMC that are kind of interesting. So in order to fix EMC, what do we normally do? We throw filters onto something to either block noise or from coming in or from getting out. And usually we just have a pile of parts and we throw them at the problem. Or you can try to wrap aluminum foil around it, or add some transient suppression depending on the type of problem you have. And if you really want to make a mess, you throw RF absorber material all over everything, and it probably doesn't work. Another good way to fix EMC is to fix the thing that's being affected by the EMC so that it doesn't care what happens to it. And sometimes changing the technology can make a big difference in how things react. One of the tools we use since common mode current, we talked about differential mode and common mode current. And for EMC, often for emissions and for picking up noise that's radiated, common mode current is the most important aspect of the way things are working. So it's good to be able to measure the current somehow. It's a high frequency AC current. So there's a technology for current probes. We actually built a current probe as part of a maker event. Some of you may have been there, but we built one a long time ago that we could use to diagnose EMC problems. And we used candlesticks and a ferrite core from ferrite. And you can see the components. You wrap wire around the core, you put it in 2 pieces, you have it inside of a metal. You have to have a shielded housing. So we made them with pieces of brass, and they fall apart after 20 years. Okay. So you can clamp that around wires, and then you can measure the amplitude. So a good way of a good problem to look at is the noise from a DC motor. DC motor has sparks in it, and the brushes are connected to wires. Let's see if I can point on the screen here. So sparks come inside the motor, between the brushes and the commutator, and they make high frequency noise, which comes out on the wires. And it's typically, you can pick these up with radios because it makes a common mode noise on both wires, which couples back to the motor housing. And that makes radiated emissions. And then because there's parasitic capacitance in the motor, you have this, coupling between the motor and noise and the wiring. So if you're trying to fix it, often, I don't know why I can't show you the top of the screen, but you can do a couple different things. You can add filters. One type of filter is to put a bypass capacitor on the wires so that they produce a high frequency shunt between the wires and the housing. And so the field of the wire between the wire and the housing is reduced, and you reduce the noise. Another way is to put a big inductance in series. So inductance, the core, provides a high impedance so that the current can't get out. It's what we call a common mode choke, so that it blocks the current on both wires at the same time. The current going the same direction in the wires at the same time. It's kind of a bizarre winding pattern. And then the capacitors, they provide a low impedance so that you short circuit the RF current. So those are 2 opposite ends of the impedance spectrum, and they both have a similar effect, trying to keep the common mode current from exiting the motor. So I have a little demo we did with a little DC motor and our current probe, and you'll see in the background the spectrum analyzer on the PC, okay? So what you want to watch when you see this video is the noise, the type of noise that the motor makes. So you look at that and tell me whether it's broadband or narrowband noise when you see it. And then tell me or think about, you'll see the solutions up here, but think about which solution will work best, and then which one will work best over a wide frequency range. So let's play the video. Okay, so here you can see motor running, clamping the probe on the wires. Both wires are going through there. You see the change in the spectrum. Measuring common mode current. So first, attached to the terminals are two little capacitors. I'm going to connect the wires of the capacitors to the housing to make bypass capacitance. The noise changed, right? It went away. Now I disconnect the capacitors, the noise comes back. See that? Now I'm going to add the common mode choke. I have to disconnect the wires to put that into the circuit. Okay. So off, the noise goes away. Put the core in. Both wires go through the core. You have to come back through the core. I loop it around so I have more than one turn. Then we have to connect it back up. Bear with me for a second. I like the background music. It's from our 16-year-old. It's like video game music or something. Okay, there it is, running again. Now look at the screen. Is it good? Yep, it's good. So both solutions worked, right? Both solutions worked. First of all, who knows what kind of noise that was? Did you see what it looked like? What kind of noise was it? Broadband or narrowband? Broadband, yeah, because it was over the entire range. You saw the big blob, right? Okay, the other little signals there that you see, those are noise that are picked up by this analyzer. And it's radio communications of some sort. And those are narrowband signals. They're always there, right? They're not from the moon. Now, all I show up there is a very small snippet of the entire spectrum you might be interested in. So now the question is, do you think that those components will work over all frequency ranges or just the one that I'm looking at? Anybody have an idea? Do you think it'll work everywhere?
No, depending on.
Probably not, right? Why not? Because the components, their characteristics aren't the same at all frequencies. So it's very important to know how your components change with frequency. And there's ways you can combine components to make it more of a broadband filter. Okay. Let's go to the next one. So we have a couple other case studies. One is something Akio is very familiar with, a light dimmer switch, right? He's our resident expert on light dimmers, okay? So he knows all about this, okay? This is, if you tear one apart, you'll find it's got these components inside, all right? And what are they there for? I mean, the only thing that makes the light dimmer work really is the trigger and the thyristor. That turns the current to the light on and off. And it makes a very abrupt transition, and that makes a lot of noise. But they added all these other components, right? Well, one way to reduce noise is using a low-pass filter, and the simplest low-pass filter is to combine an inductor and a capacitor together, right? So when you do that, it sort of spreads out the effect and makes it more of a broadband filter. And you can see in the light dimmer, there's an inductor, you see, and then there's two capacitors. You see these? So if you look at what's happening, the source on the left conducts through, when you turn the switch on, conducts through the inductor, through the thyristor when it's triggered, down to the light and back. And then that's current will go one way through there, and then it will come back the other way, right? So what we have is two filters in this little box, one for conduction one way when we have a low-pass filter, choke, capacitor, and then the other direction, which is through the choke and the capacitor going back. So you get a filtering both directions in the wiring. It's pretty cool. But is it differential or is it common mode? Now, it's a differential mode filter. So why do I call it a differential mode filter? Anybody know?
You're only filtering one side of the line.
Right, we're only filtering one side of the line. We don't have a filter on the other side, the return. Why? Because they only tried to fix a differential problem between the light and the wall sockets. So often in a house or something, that's where the big problem is. You're conducting noise all over the place. So now that was emissions. we also studied immunity a little bit. So how do you fix immunity problems? One way, you can add filters, you can add shielding, you can add transient suppression, or you can try to add RF absorbing material, right? Well, it's the same list, right? It's the same list we had for the emissions. That's because the same things work both ways, either to protect or to keep noise out. Or you can change the technology. If you go to digital, change the modulation type, those things also really do more for making your system immune than a lot of these other things. So we had this problem, and the problem was we had a computer at one end of the room and nobody would be near it. And all of a sudden it might've been asleep and then it would wake up. And we'd look and we'd say, why is it waking up? Is it like a ghost in the room hitting the button? And it would happen weird times, right? It would just be sitting there for hours and hours and hours and then just wake up. Turned out we had a dryer at the other end of the room. And whenever something would be pulled out of the dryer, like sheets or whatever, and you get static electricity, it would set off the screen. It would trigger the screen to wake up, right? So the problem wasn't a ghost, it was ESD. And it's not ESD that's hitting the computer, it's something we call indirect ESD, where the ESD is in an object over here, and the noise from the ESD, which is high frequency, radiates out and disturbs other things. In this case, it was the computer. So then the question is it the mouse? Is it the keyboard? Is it the computer itself? What's the problem? And by eliminating each part, you can determine that, but you have to have a repeatable ESD source. So I made an ESD gun with some spare parts and probably duplicate the same thing. That old screwdriver gun, and it's pretty cool. But, it's good enough to make an art. And if you take that, you can do some testing. So we did a whole lot of testing on the computer, and we found out it was the keyboard. It was a USB keyboard, right? At least we're a little bit more modern than the USB keyboard. And if you look at it with a scope, you can see normally on a USB wake up from the keyboard, you hit the key, you get a long interval, and then it starts to communicate. So when you have this ESD, it thinks you hit a key. Whoops, it thinks you hit a key. So it goes through this wake up routine. And if you zoom in, you can see a transient, which starts the wake up routine. And so we pull apart the keyboard, we look at it, and if you ever pull apart a keyboard, you see a whole bunch of layers with a whole bunch of traces that overlap because you hit a key and it connects different layers, and it ends up that you have these loops inside from the layer to layer. And so one way you can make it think you're hitting a key is to send a pulse through the loops inside the keyboard so that it thinks there's a connection of some key, and that triggers the wake up routine. Another way is it's common mode current. You can get an induced current in the wiring of the USB bus, and we found out both of these things cause the wake up of the computer. Now, if you're trying to fix a loop like on the left here, one way to do that is to put shielding on it so that the field from the shielding that's induced by the pulse opposes the impinging field so that you get a much lower field in the keyboard. And you can do that either by putting foil over the keyboard, which doesn't help, or under the keyboard. If you put it under the keyboard, you say, well, how does that shield it? It's the same way it is on the top, in some sense, because it's making a canceling field so that you have a very low field in the loop, all right? It tries to oppose whatever transient field hits it. And that's a similar thinking that drives us to put ground planes on PC boards. So there's not much difference putting foil under my keyboard or having a big ground plane underneath the keyboard, right? So it's kind of the same thing. So we had both of these problems, and they both have different solutions. One on the common mode, you might be able to fix it with some inductance, like with common mode choke, like I showed before with the motor, and the other one, shielding, right? So we did a whole bunch of repeatability experiments, carefully controlled with our ESD gun and measurements and all this. And we found the best solution for this particular, it was a desktop, was the top one here, or I'm sorry, it's the one where you get it closest with the ESD gun to the keyboard, and that's where you have beads on the wiring and foil under the keyboard, which is what's shown down here in the movie. Okay, so it's a long time ago. Tried it again with a laptop and a keyboard, another USB keyboard. Now, when you look at this, it'll show you how to fix the problem. You tell me whether you think it's common mode, differential mode that's the problem. Differential mode's the loop, common mode's the wiring, right? So watch this and you tell me what you think. There's the ESD gun down there. There's an arc, wakes it up, right? Okay, put it back to sleep. Now, we're gonna put foil under the keyboard like we did before, right? Comes the arc. The arc wakes up. That's interesting. All right, watch this. Now move the foil so it's under both. Okay. Oh, it doesn't wake up. Oh, okay, put it closer. Really close. And there it wakes up, okay? So the solution is to put the ground plane under both. Now, what do you think is the problem? Common mode or differential mode? Who knows? Anybody have an idea?
Differential?
Why do you think it's differential?
Because the loop, because I'm loop.
Well, in this case, I don't think you can be wrong either way. And I'll explain it this way. When we had the keyboard and the desktop, we had both problems. We had to fix both of them, right? In this case, I put the foil under the keyboard and it didn't work, right? But that's probably because it had both differential and common mode problems. So then I put it under both, which gives you this common ground plane, which provides a return path for the common mode current, other than through the computer. And that way, it kills the common mode problem, but it's still under the keyboard. So if there's also a differential mode problem, it'll fix that too. So you can't tell. You can't tell which one you're fixing. Am I running out of time here? I see whispering.
No,
what time is it?
It's 48 after.
Oh, I'm sorry. Yeah, I have
Well,
like
that's okay,
one
because
more, I think.
can you do it? No, just keep going because we started late.
Yeah, I have a few more minutes. We have 15 minutes built in.
Right.
Okay.
So I'll try to finish in a couple minutes. Okay, so this is another problem we had. This is the cell phone problem we talked about before. We had a cell phone in a cabinet, and we had somewhere else speakers with a computer speakers with built-in amplifiers. Every time the cell phone would periodically do something, you'd hear them in the speakers. It was like, where's this coming from? And it's like a cell phone. It's like a gigahertz or something. And how does it make a noise in a speaker? That's kind of weird. Well, doing some study on it, it's a cell phone, it's a flip phone, GSM. It uses GSM protocol, which is a pulse modulation. So they have this very high frequency carrier, but they modulate it at some low frequency to send the actual data through. And here's a demo of what it really was doing. So you do some action on the phone, like send a message. Right? How does it do that? What's the modulation, of course? It's affecting something in the speaker. Well, what's it affecting? Well, we started looking at the output. You could see the output of the amplifier in the speaker. Every time you get these pulses, you see some noise, which is the modulation right there. And then we tried it with this, once that works. Anyway, try it with this, and when you key on the walkie-talkie, all you get is this constant on the amplifier. And that's because when you key this, it's a continuous wave, it has no modulation. And so you can't hear anything because the amplifier will pick it up and you get this DC value because the output of this is constant. So if you look inside the amplifier, what do you find? A bunch of diodes, a bunch of transistors, and they all have these PN junctions. And when you put an AC signal in from some RF source, the diodes can rectify the signal, and then you get DC, and DC is what most circuits use to do things, okay? So if you make a DC voltage, a DC current inside of a circuit, it's probably gonna do something you don't really want. Now, if you know, the diode is used in radios as the detector for the RF signal. So, and you put them in something, it's gonna detect an RF signal sometimes. Depends on how big the signal is, because the diode has to be able to forward bias. So in transistors, they include PN junctions, and you end up turning on transistors, and you don't want to do stuff like that. So here's a circuit for an op amp, the one used in an amplifier for a computer speaker. They're all the same, like 741 op amp equivalents. You know, it's an old circuit, and it's filled with diodes and transistors. And so I wanted to simplify it, so I built some stupid demo to show the problem using. Here, I'll show you. There we go. So there's a transistor, there's a diode, and I had this little kit when I was a kid, and you could detach the wires and the transistors with these little springs, like so now I put a diode on the base of the transistor. What happens if that diode is forward biased? It's an electronic circuit. What's going to happen if I turn on the transistor? The LED, this is an LED. The LED will turn on, right? So if I can turn on the transistor, the LED will turn on, it'll glow. There's nothing here to turn on the transistor yet, right? See if but I can do it here. See that? Okay, so that's how the cell phone affects the amplifier, because inside are junctions which are turned on by the RF, either common mode current or by a loop. So if you see here, there's a loop that I put into the circuit. So I don't know, is it common mode current somehow that's coming somehow through this and turning on the transistor, or is it this loop? Doesn't make sense. The common mode current doesn't tend to make sense, but let's see. So look at this and tell me what evidence this video shows that it's a loop problem. And is there something else you can do with the circuit that would prove that? So I don't do that I'm not doing that in here, but we can try it on this. There it is, turning on. Okay. Now, first thing I'm gonna try is to add a beat. I put it to ground connection. Maybe that'll fix it. Maybe a little bit better, not too much. Okay. I'm going to remove that, put the wire back. I like these sprinklers, they're so easy to use, but the circuit's huge, right? Okay, and now I'm going to add shielding. Ooh, that's pretty good. I got way down next to it before it turned on, right? Pretty good. Now we're going to add a capacitor, which probably is not a good idea. You couldn't let it do that in your circuit, but okay, we're going to do it anyway. That killed it completely. And next, one more thing. put a resistor. This is another way you can fix EMC problems, is with a resistor. If you can add resistance, sometimes that helps. Sometimes you have no option, you can't add resistance and your circuit won't work. But if you can add resistance, then it can make a big difference. There's another way to fix this circuit, which would also work. And I'll tell you in a second. So the resistor worked great, right? You have to get way down there. You could also change to a different diode. So this diode, it's a signal diode, has very low forward bias voltage. So if you have one that's a higher voltage, like this is probably 0.3 volts or something. If you have 0.7, it would probably fix it also. I'm not going to go over this part. This is extra credit anyway. But sorry, we have no more time. Anyway, who has the other idea how to prove it's a loop problem besides what's in the video? What can I do to show it's a loop problem? Any ideas?
You can twist.
Yeah, I can get rid of the loop, right? If I get rid of the loop, so it's like there's no loop anymore, right? And maybe it'll work. Yeah, see, look, I have to get way down in there before it does it. So it's clearly, if I make a loop, no, it never works. Yeah, that's why I do that on video. So you can, but it's probably not that important. The loop probably is not something you really have to worry about because like all those transistors were in an IC, the loops are very small, right? So it's generally for PC boards and individual discrete components. All right, I know I've run out of time. So if you have any questions, you can see me later. Otherwise, we have to get ready for Mark's presentation. Okay, so don't have any time for questions, right?
Not at this moment. Maybe
we're gonna cut off. Well, just ask me later.
We can, yeah, or catch him at lunch.
We have enough time for a 5-minute break, or I don't know what time it is.
Well, there's 3 minutes. We have 3 minutes.
I apologize if we had to really squish things in here.
I'm sorry you didn't get to grow up with the 160 projects and one electronic kit on Radio Shack, which uses
I pretty much did have
digital.
that. Yeah, that's where I got this
Yeah.
from. I could have brought in my old kit.
Yeah.
I still have it.
Yeah. It's wonderful.
I know, it was really great. Let's see. I have to get